So we've put in a lot of work to get to this point, but we are finally ready to look at some real life applications of this stuff. So we've been studying triangles all this time. We're going to look at what are called sinusoidal functions. That's the word there. Or we can just say trig functions here. Sinusoidal means wave-like, and we'll see what these look like here in a second. So I picked a scenario we're all familiar with to start to study these models, and that is just temperature on a hot day. It's warming up some, and we're going to look at, I think this is going to end up being like a real summer day if I recall correctly. So we have this function f of t that gives us the temperature during a 24-hour period. So it says it's good from 0 to 24, so t is in hours here. And our first task here is to find the temperature at t equals 0, 12, and 24. So I can use my function notation to represent f of 0. And that, of course, means that I take out my t and plug in a 0. And now, because we know our unit circle pretty well, we can actually evaluate this without a calculator. So cosine of 0 is 0, right? So this ends up just being 80. And then I can do the same for my other 3 points, right? So f of 12, well, that would be 80 minus 10 times the cosine of 12 over 12 pi, or just cosine of pi, right? And then with my unit circle, hopefully you have this memorized. If not, you can look, right? But that ends up being 80 minus 10 times negative 1, which ends up being 90 degrees. And then f of 24, same thing, 80 minus 10 cosine. Now 24 over 12 is 2 pi. And cosine of 2 pi, well, that is the same as the cosine of 0, right, which is still 0. So again, we get 80. Okay, so that's why it's useful to know the unit circle, is because then I can start to evaluate these quickly without a calculator. And again, you can use that as a reference. You do have it memorized at this point, or pretty close, but you can use that as a reference as you tackle these. Now, finding these out by hand is going to take us a minute. So I'm going to use my graphing calculator to figure out the rest of my values here. Okay, so I went ahead and typed in my function, and I'm going to hit second and then graph to get the table, right? And here's all of the values of the function. Notice we're going by 4s. So I can start to just plot these. So at 0, I'm going to plot a 70. And then at 4, I can plot 75. And so on and so forth, right? At 8, I'm going to plot 85. And you can make this graph yourself too on your calculator using the chart. 12, I get 90. And then it starts to go back down. So I get 85, 75, and then back down to 70 at 24. So what I get is this nice little wave, right? And that makes sense because we're talking about temperature. We all know it gets hotter as the day goes on, and then at sunset it starts to cool off, right? So that's my graph f of t. And what you'll notice, right, is imagine I took an average of all of these. That average is that 80-degree line, right, which shows up in our function here. So that's what this lesson really is about, is how the functions are related to the graphs of these guys. So we're going to start to explore that a little bit. So my average temperature, again, is that 80 degrees, and that's called the midline of the function, right? So it's the line around which the temperature seems to fluctuate. And then here's what's very interesting about this. So describe what the model predicts would happen on day 2. So let's go back to my graph here a little bit. So I'm going to hit the window button, and I'm going to change my window to 0 to 48, because that would be 48 hours is 2 days. And then I know my temperature appears to be between, 70 and 90. So my y's, I'm going to change, we'll do 60 and 100, just so we have a little bit of room. So this is telling our calculator where to look for the graph. And then I'm going to hit graph. And then here's that wave I was expecting. And then it just repeats, right? And that makes sense, right? So my first wave is 1 day of temperature, right? And then it cools off at night. And then next morning, it starts to warm up again, hits a maximum temperature, and then cools off again, right? So what we get is this like repeated cycle, right? So the cycle repeats on day 2. So that's why these guys are useful, these types of functions are useful, is because they model what we call periodic phenomena. And really that just means things with a repeated pattern. We'll also note that they have a wave-like shape. And that wave is around a sort of center, right? Oops. So that wave is around a midline. Okay. So here's a real life example. On the next page, we're going to take you back to basics a little bit and just look at the plain old graphs of y equals sine x and y equals cosine x. Okay, so we're going to look at just plain old y equals sine x. So our last example was a little bit more real life, but a little bit more complicated, right? So we're going to look at a basic example to see if we can't figure out some of the features of these guys. So what we can imagine here is imagine I'm looking at my unit circle. Remember, sine is the y values of the unit circle. So imagine I walk around the unit circle counterclockwise, and then I just graph all the y values, right? So at pi over 6, I graph 1/2. And then pi over 4, I graph root 2 over 2, and so on, right? So what that ends up looking like is we get 0, 0, and then pi over 2, we get 1. At pi, we're back at 0 again. At 3 pi over 2, we're down at -1. And then 2 pi, we're back at 0. So again, we can start to see that wave shape, and this cycle just repeats. So you can kind of fill it in just based on the pattern, because you guys are good at recognizing patterns. And that's our sine wave. So as I draw, you should get a nice smooth curve. And it's tricky on the computer screen for me, but you should get a nice wave through all of your points. And then if we look at cosine, what we'll notice, right, because cosine spits out all the similar values, we'll notice we're going to get a really similar shape. Except it's shifted a little bit. So cosine is my x values. So instead of starting at 0, I start at 1. Pi over 2 is 0. Pi now is -1. And again, I'm just pulling the values off the unit circle. So pi over 2 is 0, -1. 3 pi over 2 is back to 0. And then 2 pi back to 1. So there's my cosine graph. Again, the same graph as my sine graph, just shifted over a little bit because cosine spits out slightly different values as we walk around the unit circle. Now, more generally, what we saw, right, in our previous example, is we can kind of shift these guys around a little bit. So this 80 added in, shifted my graph up to 80 as my center line. What we'll start to explore here is these 3 parameters. So I have A, B, and C. And that will be your first mission, is to fill out these things while you're working through delta mass. So you'll start to explore how these parameters A, B, and C affect the shape of our graph.